grade 12s, we are in unit number 5 for the second lesson, and this is module number 25. And number 25 is going to cover pages 15 to 20. Okay, it's not too tricky for this concept. After you've been able to do this topic and you've done, maybe try a couple of textbook questions that go along with it, you'll be able to complete questions 4 and 5 in the review package. Okay, so that was the review package. And again, if you don't have a printer, that's okay. Just summarize the questions and then practice, right? So now we're at number 4 and 5 for being able to complete those. So this is called the solubility equilibrium topic, and when we calculate solubility of something, we have to remember what we're talking about. We're talking about salts that set up a system that it reaches equilibrium. So when does that occur? Well, that's going to occur when you dissolve salt into a solution. So you're thinking of an ionic particle and you keep adding it to water and adding it to water. At some point, it reaches a saturation point where you can no longer add any more salt to it and it will dissolve. Okay, so when it reaches that equilibrium, when equilibrium is established, it's because you've set up a system where it is now saturated. So if you look at this example I've got here with lead 2 iodide, when it reaches the saturation point, it's at equilibrium where the rate of dissolving is equal to the rate at which that substance crystallizes. Remember, it's a dynamic system, so it's occurring all the time. It doesn't look like you're able to dissolve anymore because it's reached saturation. Okay, how much does it dissolve? Well, when it reaches an equilibrium, you could calculate a K value, a constant, that is particular and specific to a specific temperature. So let's have a look. What would that look like? Here are some equilibriums that would be established in saturated solutions. So you can see silver chloride sets up an equilibrium where the solid goes to the aqueous ions, and you know how to dissociate based on the ratio of the ions. So that's something you're all familiar with, right? Recognize the fact, like for this one down here, it's silver phosphate, and for every 1 particle of silver phosphate, you would get 3 ions of silver for every 1 ion of phosphate. And you're thinking ahead that you're going to calculate K, which means it's going to be the concentration of your products over the concentration of your reactants. And of course, those concentrations have to have an exponent if there's a coefficient in the ionic ratio. You'll also notice that on the reactant side of these equilibriums, you have a solid. And do we ever put a solid substance into our equilibrium expression? No. So for all of these, where we calculate the KSP, you can see that when you're calculating KSP, and again, it's called the solubility constant product, solubility product, and the K has a little SP, right? We've already done KE, but now if we're talking about dissolved and solubility of ionic particles, you're going to put a little SP beside the K, and you can see that you can write the expressions, okay? So for the first one down here, see how there are 4 up above? These are the 4 down below. So you can see for the first one, for the silver chloride, it would simply be the concentration of the silver ions multiplied by the concentration of the chloride ions, and that concentration is going to give you a K value. So you can calculate K if you know those ion concentrations at equilibrium. And of course, again, at equilibrium is when you've got a saturated solution. KSP for the third one, can you see that that exponent on the 2 for the chloride ion comes from the fact that for every 1 lead 2 chloride, you get 1 lead ion and 2 chlorine ions. So can you see what you're going to do for the silver one? Silver phosphate. Okay, let's practice. Practice writing your KSP formula, because of course you're going to be solving for that. You've got your silver ions to the exponent 3. Multiplied by the concentration of your phosphate ions, and that's how you would calculate the KSP value. So what I want you to do now is take a little time the video, pause it, and I want you to write the formula for all of the ionic salts that are in the table. That's the easy part. Then you're going to write what the equilibrium expression is. Then you write what the KSP value will be, and then you can look it up in a table in the textbook what that KSP value is. And what you want to remember is it's the KSP value at 25 degrees. That's the value that you get in the table in the textbook. So if you were to calculate the KSP in the lab, for example, and you didn't get the actual KSP value that it says in the textbook, one experimental factor that throws it off, an error, if you will, could simply be the temperature, because K is temperature dependent. And if you think about it, you already know that, because if you're dissolving a salt in a beaker of warm water, isn't it going to be different? You can dissolve more than you would if it was in a beaker with cold water. Okay, does that make sense? All right. That's page number 15. So moving on, what are we going to do with this information? Well, we can compare the K value, because up until now, we've only really talked about salts where they're very soluble. Ionic particles are soluble. Here's the good solubility table rules that we've learned, which one's more soluble than others. And now we can say, let's take that K value and compare them. Okay, so you'll notice that the values are the ions that are the ionic compounds that are in this table. These are the ones that are slightly soluble. Okay, they set up an equilibrium a little bit faster, don't they? Because they don't dissolve very much. So then you have a lot more solids sitting there sooner than you have with the ions. So here's where we add a layer to our understanding of ionic particles. If you were to compare lead 2 chloride, and copper 4 sulfide, which one is most soluble and least soluble? Well, I highlighted them in the table up here. Have a look at the values you get for KSP. Clearly, a bigger KSP value is going to be one that's more soluble. Mathematically, does that make sense to you? It should, because you're going to have more ions if it's soluble. So therefore, you're going to be able to get a value that's actually bigger. So if you're comparing these two values, just remember the fact that 10 to the negative 5 is a much bigger number than 10 to the minus 48. That is teeny tiny, right? So which one is more soluble? If you're comparing those two, which are both very slightly soluble, then you can get a calculation there and figure out that your PbCl2 is most soluble. Why? Because it has a larger KSP. Okay, you can compare these, and it's very easy to compare solubility values if your ions have the same ratio. If you've got cation to ion ratio, and this is an example here where you've got a 1-to-1 ratio, a 1-to-1 ratio. If you're comparing the same things, then you can compare the KSP. When the ratios are identical, then the salt with the larger KSP will be more soluble. So if you're to compare these two, silver chloride and copper 2 sulfide, the number that is the bigger value, if you're comparing these two, is the silver chloride, and it has a bigger KSP, so it's going to be more soluble. Now, if you are looking at cation to ion ratios that aren't identical, okay, then the KSP value isn't always indicative of relative solubilities, so you might not be able to use them to compare. So that's why there are limitations to using the solubility table, and here they are. Limitations when you're using the solubility table and general solubility rules to predict whether a precipitate forms. Well, the precipitate's only going to form if the concentration of ions is at or above the saturation point. If it's unsaturated, then no precipitate's going to form. It varies with temperature, and it's limited to predictions that are at 25 degrees. So here's where, again, we add in another layer. You may know that there's a single displacement or a double displacement reaction taking place. But then how do you know if the product that forms is soluble or insoluble? Well, you look at the solubility table. But what if it's one that's soluble, but it's very, very weak soluble? And if the solubility is slightly soluble, you may not have enough ions there to actually make a precipitate. Does that make sense? Because if there's not enough ions there, they can't always make a precipitate and you can see it. So it makes it a little bit tricky. Okay, that's just something to think about as we carry it into the next topic. All right. I want to review quickly what the charge of the ion has to do with the strength of the ionic bond. And remember, you've already seen this page. This page was page number 17. Well, it's page number 17 in this note, but it was page number, I'm not sure the page number, it was unit number 1, page, day number 5, sorry. And when we calculated the strength of this ionic bond, at that time when we were in unit number 1, we said, doesn't it make sense that it's going to be related to solubility? We were relating it to the strength of that ionic bond. And now we're just going to add in, if you can't remember that, we're going to add in the fact that if you've got a really strong bond, excuse me, that strong bond is going to be one that's less soluble than a bond that's weaker. So here's where we come into that factor of, well, you have things that are slightly soluble. They kind of dissolve. And if they only a little bit dissolve, then that bond must be very strong because it's holding it together. Okay? How do we summarize that? Remember, we've gone over this, I know. But if you look at the very bottom little summary that I've got in our notes here, you're calculating the F value. F is the force that holds those two ions together to create that ionic bond. If you have a weak ionic bond, you could calculate that by having a small f. And how do you calculate the F value again? That's our formula. F is directly related to the charge of the ions over the radius between the center of those two ions. Okay, so the charge and the radius are the things you're going to look at with regards to the ion to help you determine the strength of that ionic bond. And if you end up calculating that F to be small, that means you've got a weaker bond. And how do you get a weaker ionic bond? You get it if you have small charges, small charge difference between them, +1, -1 maybe, sodium chloride for example, and you have a large radius. So if you have small charges and that radius is far between the center of those two ions, it creates a weaker ionic bond. Now remember, ionic bonds are always strong compared to covalent bonds, but now we're just comparing the strength of the ionic bonds. So if you have small charges and they're farther apart, it's going to be more soluble because it takes less force to break those. And that's what you're breaking. You're referring to the intermolecular bonds breaking when we're doing solubility. If you have a large charge difference between those two ions and a small radius, that creates a very strong bond, a large F value. And if they're held together with a stronger ionic bond, then they're going to be less soluble, slightly soluble. Okay, so you want to go through and you want to make sure you understand the solubility as it relates to ionic bond strength. Okay, you ready to take that into the next part? All right. Let's take that into what this means for this slightly soluble, okay? So again, what's our review here? What's our review for ones that are have good solubility? And then we take that, talk about the F value, stronger F, higher melting point, boiling point, and lower solubility simply because of that charge. So this top part of the note explains where you have good solubility with these ionic compounds and you have insoluble or lower soluble or slightly soluble for these compounds, okay? So they're held together with a smaller distance, a smaller radius, and those ions have charges that have a bigger difference between them. So they're greater than the +1s or the -1s. Okay, next you want to fill in this part here, the effective temperature on solubility. I think that's fairly easy. We've gone over that many times. So why don't you just fill this in and then just make sure you review that and see if you have any questions because I want to start doing a calculation. So this is the example down here. Let's see how we could calculate something that is slightly soluble. It experiences an equilibrium because it gets the saturation point very quickly because you put it into a beaker and all at once you can hardly dissolve any of it. So how are you going to calculate that? Well, if you've got an expression that looks like this with our calcium phosphate, it sets up an equilibrium. For every 1 calcium phosphate, you have 3 calcium 2 plus ions and 2 phosphate ions. They're fairly large, right? They have big charges, so therefore they have a weak bond. Therefore, they are slightly soluble, strong bond, and therefore you're going to have very little of them that are going to dissolve. So how do you calculate that? You set it up to calculate the Ke, which is really the Ksp, right? Because now we're going to talk about solubility constant, but you set up your K value and calculation the exact same way. Now, shall we start to do a question? Okay, so let's do a question here where we've got sodium nitrate. Under most normal circumstances, soluble ionic compounds are rarely present at the saturation concentration. They therefore not involved in an equilibrium. And you know that, sodium nitrate has good solubility. You get 100% dissociation and it doesn't set up an equilibrium. So the concentrations of the sodium ions and the nitrate ions are below that saturation point. So that would not be an equilibrium example. So you would just show 100% dissociation, and they do. The concentration of this is the concentration of this and the concentration of this. That's the easy ones. So what do we do if we have something that is slightly soluble? Okay, and here's what the question sets up like. It says, what is the molar solubility of ferrous hydroxide? It tells you what the molar solubility is, and you're going to calculate the Ksp. So what does that mean? It means do your balanced chemical equation first. Okay, you're going to show that it sets up as an equilibrium because it's slightly soluble, so it reaches equilibrium. I'm going to have 1 Fe2 plus ions to every 2 hydroxide ions. Okay, and so I'm going to write this Ksp, I'm going to write my equation and with my calculation of how I'm going to figure out those concentrations down below. So at equilibrium, if this is 2.31 times 10 to the negative 6 moles per liter, for every one of these, I would have one of these. So 2.3 times 10 to the minus 6 moles per liter, and I have 2 times 2.3 times 10 to the minus 6 moles per liter. So the concentration of my hydroxide ions, can you see here, is 4.62 times 10 to the negative 6 moles per liter. So when I calculate the Ksp, I'm going to write my formula like I would. I take everything that isn't a solid or a liquid and put it into my formula. Concentration of the products and any coefficients that you have turn into exponents over nothing because that is 1. And I pop my values in. Okay, 3,1 times 10 to the minus 6. My hydroxide ion concentration is twice as many because for every iron 2 hydroxide that dissolves, I get 1 ion of iron and 2 ions of hydroxide for 4.62 times 10 to the negative 6. And that is still squared. Calculate the K value and it would be 4.93 times 10 to the negative 17. That is calculating the Ksp given the solubility that you know. Now, what if you have to go and reverse that? So question number 2 down below here is now, let's take the solubility information from the table in the textbook and calculate the molar solubility. Part A, calculate what the solubility is. So it's moles per liter. The second part of the question asks you to convert it into grams per liter. So this is where you're going to have to do a couple of these questions from the textbook, okay? Do some of them. It tells you in the schedule which ones are associated with this, but I'll just show you the example that I've already done and just talk through it, okay? So 1 calcium phosphate goes to 3 calcium 2 plus ions and 2 phosphate ions. So my ratio is 1 to 3 to 2. So now I know what my K value is. That came from the textbook, and I'm solving for X, okay? 3X, where'd that come from? Right there. 2X. And yes, you still have to put your exponents because the exponents refer to the coefficients in my balanced equation. Remember, this is slightly soluble. You're going to end up with very small numbers. Mathematically, does that make sense? Go back to the first one. Iron hydroxide, yeah, not so soluble. 4.93 times 10 to the negative 17, it hardly dissolves at all, right? Slightly soluble. That's the KSP. So, what about calcium phosphate? Solve for X, and you end up with 1.1 times 10 to the negative 7 moles per liter. Okay, that is my X value, and that is calculating the molar solubility. How soluble is it? Not very. 1.1 times 10 to the negative 7 moles per liter. So again, just make sure you understand that terminology. What are we calculating? Molar solubility. If you were to express that in grams per liter, all you need to do is calculate your molar mass. Once you've got your molar mass, then I take my moles per liter, multiply it by my grams per liter. Do you see that? Your moles would cancel out, and you could express that molar solubility in terms of grams per liter, which is something that you would do when you're talking about another way to just explain and look at that concentration. Okay, so that was a lot for today. We did molar solubility. We figured out how to calculate the KSP. We looked at things that were slightly soluble, and why? Because of those ionic charges that you have that create those strong ionic bonds or weak ionic bonds. And so if you have a strong ionic bond, then not very much of it will dissolve, and you can establish a saturation point much sooner. So what's the concentration of an ion that dissolves in a solution? Well, then you just factor that into the KSP and be able to calculate it. Okay, so good luck with that. That's the calculation of KSP, and that's it for today.